Okay, I'm going to do the answers here to the homework. And this is kind of interesting stuff. And I think that equilibria at first is a bit of a challenge. So here we have a situation. Notice that our arrow is two-sided, meaning the reaction goes backwards and forwards. And which direction it's headed in can be influenced by adding or subtracting things from the situation, from the system. So in the first one, if the amount of hydrogen is increased, so if I add more hydrogen, that is going to cause the system to want to get rid of the hydrogen. So in order to get rid of the hydrogen, it is going to shift equilibria to the left. It always wants to release the stress to not have that extra stress in it. So it will do that. Now, the second thing we'll take a look at here is, let's use a different color here. We'll use green. The pressure of the water is increased. Increasing the pressure of the water, which is a gas, is just like adding water. So if I add water, it is going to try to get rid of the stress of that added water by getting rid of it and pushing the equilibrium to the right. So again, our system always wants to get rid of that added stress. If the amount of oxygen is decreased, so I'm going to take oxygen out of the system in order. If I've done that, now the system wants to restore the oxygen concentration. So it is going to then try to recreate that oxygen or create it by shifting the equilibrium to the right. So again, our equilibria is always going to shift to try to decrease the stress of the situation. Temperature is increased. Think of temperature now. Think of temperature as energy and just as a whole nother reactant, just as something else there. So I'm going to add heat. If I add heat, it's going to try to get rid of that heat. So it's going to push equilibrium to the right to get rid of or dissipate the heat. Now, the next one, the volume of the container is pretty straightforward, but it does involve a little bit of counting. Now, the volume of the container affects gases. On this side here, we've got two gas molecules, two water in the gas phase. On this side here, we have more. We have three. So here we have two gas particles. On this side, we have three gas particles. So if the volume is decreased, in order to keep the pressure constant, it is going to try to go towards the side that has less gas on it to keep that pressure constant. Lastly, a catalyst. A catalyst has no change on equilibria, so it's interesting. Does it speed up the reaction? Yes, but it doesn't cause the equilibrium to shift either towards the reactants or the products. So catalyst never does anything for us here. Here is a second situation. On this one here, we've got liquid water and we have water vapor. So this is it's absorbing energy, and so it's endothermic, because it's absorbing energy. So if I increase the pressure, because there's only gas on this side, it is going to try to get rid of that increase in pressure by pushing equilibria to the reactant side. If we decrease the pressure, so we take pressure off, it's going to have the opposite effect. It's going, why is this not going red? I want you to be red. Come on. Here we are. Increasing vapor pressure is going to have the exact same effect. It is going to push to get rid of the gas so that it can keep pressure constant. Decreasing vapor pressure is going to try to restore the amount of vapor so that it keeps pressure constant. Remember, we're trying to keep the same condition, so we're going to get rid of whatever stress it is. If we're going to increase the temperature, it's going to try to get rid of that heat. Think again, heat as a reactant. So increasing temperature is going to go to the side without the heat. And if we decrease this, if we get rid of the heat here, we make it colder. So if we take heat out of the system, it's going to try to restore that heat by pushing across like that. It's going to try to restore. Remember here, we're always trying to restore or return equilibrium, always trying to get back to equilibrium. So number 3 had iodine crystals and iodine vapor. So the difference here is we've got solid on this side, we've got gas on this side, and you have to heat up the solid in order to vaporize it. So the effect of reducing temperature, if we take energy out, if we take temperature or heat out, it is going to try to restore that heat. So it's going to push equilibrium towards the reactant side. And think of it logically. What is the effect of reducing temperature? It's going to freeze the iodine solid because you're removing energy. So it is trying to restore the equilibrium. Now, if we reduce pressure, because the gas is only on one side, so if we reduce pressure, that will be a bit different. So we're going to take our pressure off. That is going to slide things towards the product side as the system tries to retain or restore pressure by producing more gas. So again, we're thinking about directions here, and that if we're reducing the temperature, it's going to try to restore the temperature by shifting equilibrium towards the reactant side. If we're reducing the pressure, it's going to try to restore the pressure by pushing things towards the product side, which is the only side with a gas on it. Number 4, ice in equilibrium with liquid water. What is the effect of reducing temperature? So if I take heat out of the system, it is going to try to restore it by pushing equilibrium towards that side. Does that make sense? Does liquid water freeze to a solid when you take heat out of it? Yes, student, it does. So that's the effect on reducing temperature. It tries to restore the equilibrium like that. And number 5, this one here, a little bit tougher. I want you to note something right off the bat here, and that is that this is a solid. So that means that we've got gases and solids, and that solid is treated a little bit differently. We don't actually consider it when we are doing these problems. We don't consider solids. So indicate the effect of the following stresses on equilibrium. If we add carbon monoxide, so we're going to increase the amount of carbon monoxide. So I'm dumping carbon monoxide in here. It is going to try to restore equilibrium by pushing it towards the reactant side to get rid of the excess carbon monoxide. What else could we do here? In the next part, it says adding oxygen. So if we add oxygen, it again wants to get rid of the oxygen, so it's going to produce more product. So again, by adding things, it tries to restore equilibrium by getting rid of it. The addition of solid carbon, nothing. Why? Why? Because it's a solid. Solid things have a concentration of 1, and we don't count them in these things. So addition of a solid is not going to change our equilibrium constant. Now, if we decrease the volume of the container, we've got 1 gas molecule on this side, we've got 2 gas molecules on this side. It wants to keep the pressure constant. So if we decrease the volume in order to keep the pressure constant, it is going to try to go to the side with less gas on it there so that it can keep the pressure constant. All right, those are the explanations as to the why of it. I think this is going to take some time coming along, but equilibrium is the response to stress. And that, like Professor Dave says in the video here, I'm going to do a little bit of this with you today, and we'll go on with it, and hopefully we'll be picking it up. I hope you're doing great. Take care. Bye-bye.